Hi everyone. My name is Douaa Al-Assaad, and today I'm going to be talking to you about a quantitative assessment framework that was developed to assess the IAQ resilience performance of ventilation system, and with a special focus on smart ventilation system. So, as we know, smart ventilation systems can adjust ventilation rate by time or by location to provide us with good breathable air quality while also being energy efficient. And they are always designed under expected indoor and outdoor pollution loads. However, throughout the building's lifetimes, there occurs unexpected disturbance event or shock events that are sudden that can cause a reduction in the system performance. Thus, the indoor space can shift it drastically from its IAQ design conditions. So we can have an accumulation of harmful contaminants and an acute exposure of occupants to these harmful contaminants during a very short period of time. So it's not enough for our system to be able to function under these expected conditions, but it should also be able to do so under unexpected disturbances or shocks. And this is what we mean by IAQ resilience performance. So basically, our system needs to be resilient. So I also talked to you in the beginning about disruptive events. So how can we classify these disruptive events? What are they? So first, we have mechanical disruptions that occur to the components of the ventilation systems and that can cause a partial or complete disruption in the operation of the system. This can be due to a lack of preventive maintenance, inadequate fault diagnostics techniques. And for example, this can be fan failures, power outages, fouling filters. Second, we have internal disruptions that occur inside the building envelope due to an excessive indoor pollution event. This can be due to an excess of occupants in the space beyond the capacity of the air handling unit, or it can be infected people, just like what we saw during COVID-19. And third, we have external disruption occurring outside the building envelope due to outdoor pollution events, excessive outdoor pollution events, such as an outdoor fire or traffic jams, which cause an increase in the supplied amount of pollutants through the supply air of the ventilation system. So I also talked about the resilience performance. So it's very important to determine all the aspects of resilience performance in order to be able to quantify it. So in this figure, we have a theoretical temporal evolution of a certain concentration of a pollutant P when we have a shock event. So when the shock event occurs, the concentration of the pollutant will build up. The absorptivity time is defined as the time it takes for the concentration to cross a threshold reference value established by guidelines and reach a maximum value. The recovery time is the time it takes for this concentration to go from that maximum back to the reference value when the shock is over. And we also have the degree of impact, which is how much pollutants are we inhaling during that period of the shock. And we see here in this figure that we have multiple profiles, and that's because these three aspects can change depending on the type of ventilation system, depending on the type of control, the building envelope characteristics, or occupant behavior. So now I want to define to you the resilience score. The first step was to quantify the shocks or disruptive events through the degree of shock. So shocks are characterized by both their severity or intensity and their duration. So degree of shock combines these two characteristics. The duration is simply the time of the shock normalized by the occupied period, while the severity can differ based on what is the type of or the class of the shock. So with mechanical disruptions, the severity is defined as the deviation of the ventilation rate compared to what is expected. When we have internal disruptions, it is a deviation of the internal pollutant loads compared to what is expected. And in case of external disruptions, it is the deviation of the concentration of pollutants in the supply air compared also to what is expected. So combining severity and duration, we can quantify shocks using the degree of shock. The second step was to quantify the different resilience aspects that I spoke about at the beginning. So with the absorptivity, we normalize the absorptivity time with respect to the occupied period to obtain the absorptivity effectiveness, an index that varies between 0 and 1. The higher it is, the slower the absorptivity time, which is desired, so the better the absorptivity performance or effectiveness. We have the recovery effectiveness, which is 1 minus the recovery time capped by the occupied period, also varies between 0 and 1. And the higher it is, the faster the recovery time, which is desired, and the better the recovery performance of our system. And finally, we have the resilience effectiveness that quantifies basically the degree of impact. So how do we do this? We benchmark or we compare the ppm hours of the system under shock, and we compare it with respect to a reference case, worst case scenario without any ventilation. So if the ppm hours would approach this reference case, the ppm hours of this reference case, this means that the effectiveness is closer to 0, which is very bad. And if the ppm hours of the system under shock approaches that of the ppm hours of the system under normal operation, this means that the shock is not felt by the system, which means that this index will be closer to 1 and better resilience effectiveness, which is what we want. So now, having these three aspects quantified, we juxtapose them or we plot them on a radar chart or spider chart, and the resilience score of each contaminant or pollutant is nothing but the normalized area of the triangle formed by these three aspects. And then the total resilience score is the summation of all the individual resilience scores of the different contaminants. So note here, in the resilience score, we make a distinction between CO2 and other hazardous air pollutants, because basically CO2 is not a contaminant, but just a measure of ventilation effectiveness, so we keep it on the side. While for the other hazardous air pollutants, we sum them up on their own, and we multiply each of them by a weighting factor depending on the level of harm. And how do we determine these weighting factors? Well, we do that by combining a qualitative and a quantitative approach. So in the qualitative approach, we start by ranking the contaminants on a ranking of 1 to 5. So based on their level of hazard causality. So a ranking of 1 means that there's high evidence found by international agencies that this contaminant has high evidence of harm on on both humans and also animals. And the more we go higher in the rank means that the probability of evidence or the evidence of harm decreases. So with the qualitative approach, we pick the substances that have a ranking of 1 or 2. And then we move on to a quantitative approach where we calculate the hazard quotient, which is a ratio of the mean exposure concentration over the threshold values established by guidelines. And then we see if the mean concentration of the hazard quotient or its 95th percentile, how much do they cross 1? We can thus weigh the different substances with respect to each other such that the weighting factor summation of all of these substances is equal to 1. So now that I have defined to you the resilience score, let's apply it on a case study to see how it works. So the case study that we used is a real-use educational building equipped with demand-controlled ventilation driven by CO2 demand. We modeled this building in Modelica, using Modelica, the model you can see below, and we validated it in one of the classrooms by measurements of temperature and CO2 concentration under normal operation and also under a case of power outage. So after validating our case study, we did a lot of simulations. I'm not going to show everything, but some of the scenarios are a demand-controlled ventilation, which is the status quo of the building, a constant air volume, and the demand-controlled ventilation without any filters. We simulated a mechanical shock of power outage, varying between 30 minutes up to 7 hours, which is the full occupied period of 1 day. We have an internal shock, which is an increased amount of excessive occupants in the space, varying from a minimum of 5 occupants up to a maximum of 50 occupants, additional occupants. And we also did an outdoor shock varying from a minimum of 20% increase in the outdoor pollution levels up to 100% increase in the outdoor pollution levels. And the contaminants that we simulated were CO2, VOCs, PM2.5, and PM10. So now coming to some results. So in this figure here, you see the radar chart I previously talked about for a power outage of 3.5 hours for a CAV system, the DCV and the DCV without filters, and you can see them for the different contaminants. Now, if we look at carbon dioxide, CAV and DCV had the same absorptivity, recovery, and effectiveness, which is expected because a demand-controlled ventilation is driven by CO2 demand, so they will function in the same way. While with VOCs, we noticed that they have the same absorptivity, but the DCV has better recovery and the CAV has a better resilience effectiveness. And this is expected because with DCV, it is driven by CO2 demand and not VOC, so it doesn't always function at the maximum flow rate, such as the case with CAV. So we have more buildup of VOCs, and thus the DCV is always recovering from is recovering from a case that was already from a situation that was already not so good in the first place, which is why we see this behavior. And with the particulate matter, CAV and DCV behave in the same way. And the DCV without filters, we noticed that it had significantly lower resilience effectiveness. Now, how does this translate to the resilience score? So here we see the resilience score varying as function of the degree of mechanical shock or increasing power outage duration. Overall, we see that CAV and DCV have the same resilience score. They, at the end, they had the same performance using this framework. However, the DCV without filters has slightly lower resilience score, and that's because of the effect of the particulate matter. So now also I will show you the results of the internal disruption. So also the same. So this is for a maximum internal disruption for CAV, DCV, and a DCV without filters. So with CO2, we noticed that the CAV has better absorptivity and faster recovery than the DCV. And this can be due to the fact that with demand control ventilation, we have a response time that is slower than the CAV, which is why we see this behavior. As for VOCs, we noticed that anyway, they had the same very high resilience effectiveness in both systems. And that's because with VOCs, when it comes to internal disruptions, we do have an increase in the emission rates, but this increase in pollutant load of VOCs is not as significantly pronounced as is in the case of CO2, which is why we don't see that much effect on the resilience performance. And finally, with the particulate matter, it was only challenged with the case of DCV without any filters at higher shock intensities. So how does this again translate on the resilience score? We see that up to a degree of shock of 0.4 corresponding to around 20-25 additional occupants, the DCV performed better than the CAV, but beyond that, the CAV had higher performance. So this gives us an idea on how we can operate our building, how we can operate our system when we have a shock that occurs. And also it gives us reason to think, for example, when it comes to DCV, about how can we design the DCV, how can we design the minimum flow rate in demand control ventilation to face such shocks. So finally, to conclude this presentation, I presented to you a resilience score that was developed to assess IAQ resilience of ventilation systems. We compared smart versus conventional systems, and we found that in the face of mechanical shocks, smart and conventional systems had the same performance. In the face of internal shocks, the conventional had better resilience performance. And in the case of outer shocks, which I didn't show, the smart had better performance, better than the conventional. And this is because with conventional, it is blowing that air at maximum airflow at all times, bringing in all the pollutants from the outside, which is expected. So with filters, there was no pronounced effect in the case of mechanical and internal shocks, but more so in outdoor shocks. So finally, this framework that I presented to you was only tested, it's very new, and it was only tested on one case study. So to improve it, it should be tested on more case studies, different building typologies, residential offices, and also more systems such as mechanical extract, natural ventilation, also personalized systems like personalized ventilation and exhaust, and other smart control strategies such as model predictive control. And also we need to test the effect of occupant behavior, and we can use this to improve our resilience score even more. So with that, I would like to thank you all for listening, and I would like to introduce our next speaker, which is Zakaria Kabara from Antwerp University, Belgium.